So in this lesson, we are going to now solve our implicit derivatives, but now starting related to real world functions. So not just graphs, right? Like with X and Y. So again, like remember, derivative is slope, right? I mean, it's slope of a tangent line, but it is slope or rate of change. So like, for example, water in a storage tank is decreasing at a rate of 8 gallons per minute, right? So it's decreasing at a rate of 8 gallons per minute. So we would write this, if we wanted to write an equation that it's decreasing at 8 gallons per minute, y is equal to negative 8x, because the rate of change or slope is negative 8 gallons per minute. So if we were to write it in the form of a derivative, it's the derivative of g, right, our gallons with respect to time, in this case, minutes. And that derivative is equal to negative 8. That is our slope. So then here, a car is traveling at a constant speed of 75 miles per hour, right? So we would write this as 75x because the slope or rate of change is 75 miles per hour. So the derivative is the derivative of m for miles with respect to time, so hours, is 75. That is our slope. So again, derivative is the slope, that value here. So like going through to solve again for these values, the derivative. So we did this a little bit going through a point. So kind of that same idea here, where instead of a point, we'll be given the values to plug in. So here again, we would differentiate just like before. So this would be 2y dy dx is equal to 12x cubed plus 6, right? Because we're differentiating with respect to x, right? We're finding dy dx. So then now here, we're going to do the same thing, right? Because what we're doing is we're going to eventually get to real world application. And that is going to a lot involve not with respect to x, if you think about like the x-axis, but think about it now as over time, right? So we always have with respect to time. So instead of our x, we're now talking about time. So here we would do the same thing. We're going to differentiate the equation with respect now to time. But now that means we're no longer going with respect to x. So you know how like we would have dx over dx? It is it's now with respect to dt. So here, again, we're going to differentiate, but now with respect to time. So same thing, I've got 2y, that was the derivative of y, but now with respect to time. So notice now here, dt is equal to 12x cubed. We took the derivative of x, but now this is with respect to time, plus 6. Notice again, we took the derivative of x, and that is with respect to time. So this is now our equation here. Notice how it doesn't cancel out because we're differentiating with respect to time. So now we're going to use this differentiated equation to solve. Given, we're going to solve for our dy dt, but given x is 1, y is 3, and dx over dt is equal to 2. So we've got 2 times y, or 2 times 3 dy dt is equal to, because that's what we're solving for, is equal to 12 times x, which is 1 to the third power, times. Now what is dx over dt? 2 plus 6 times dx over dt, which is again 2. So notice how we have these values because we know what the slope is. The slope is 2 with the variable x. Now let's simplify. This is 6 times dy dt, which is equal to here 24 from 12 times 1 times 2 plus 12. So really we've got 6 times dy dt over is equal to 36. So now to solve, we're multiplying by 6, so divide by 6. So that means here the derivative of y, but with respect to time, is 6. You're given one derivative, we're solving for the other. So here, let's do this one. We are again now differentiating our equations with respect to time. So g, so we're going to take the derivative of g, which is just 1. So dg over dt, because that's just 1, is equal to, well, that's just derivative of h is just 1. So 1 or dh over dt minus derivative of h here. So 5h to the 4th. But again, dh dt, because this is with respect to time. Now we're going to solve. So here I've got, this is what we're solving for, so it's nice, it's already equal to it. What is their value here? dh over dt is 3. Our slope is 3 minus 5 times h. Well, what is h? 2 to the 4th power times, again, what's our slope here? 3. Now notice we're just simplifying. So the derivative of g with respect to time is, so here I've got 3 and 2 to the 4th is 16. So 16 times 5 is 80, so minus 240. So here we've got negative 237. That is our slope. Here again, we're going to take the derivative with respect to t. So 2x dx over dt plus 2y dy over dt is equal to 2z dz over dt. We are going to solve for dy dt. So keep that in mind. We're solving for the derivative of y with respect to t. So here we are given, so we've got 2 times x, which is 3 times our slope of x, which is negative 1, plus 2 times y. Well, y is 4, and then we don't know our slope of y with respect to t. That's what we're solving for, is equal to 2 times z, which is, oh, I'm sorry, I forgot to give you guys the value for z here. I just realized that. Sorry about that. Z is actually equal to 1 in this case. Sorry, that didn't come out. So 2 times 1 times the derivative of z, which is 5. So now we'll go through and simplify. Here I've got negative 6, then plus 8 dy dt is equal to 10. So now notice here, we're solving for dy dt. So we need to add 6 to both sides. So now I've got 8 dy dt is equal to 16, and then divide by 8. So the derivative of y with respect to t is equal to 2. So go ahead and pause the video now and try the try on your own. And here we go. So we've got 2y dy dt, right? Because with respect to x is equal to 2x dx dt minus 2z dz dt. So now let's go ahead and start substituting because we're looking for the derivative of y in terms of t, which is here. So 2 times y, which was 3 dy dt, is equal to 2 times x, which is 5, times the derivative of x, which is -3, minus 2 times z, which is 4, times the derivative of z, which is -6. Now it's all about simplifying, right? So here I've got 6 dy dt is equal to -30 plus 48 from negative times negative. So I've got 6 dy dt is equal to 18. Divide by 6 because that's what's being multiplied. And the derivative of y with respect to t is equal to 3. So now here's area formula. Now notice though, we're having to use product rule because this is L times W. So again, derivative, well, that's just derivative of area with respect to time is equal to the derivative of L is just 1 times W. So it's just W, but we took the derivative of L. So times dL dt. Then plus, now we would take the derivative of W, which is again just 1 times L. So L, but we took now the derivative of W times dt. Now we simplify here. We're looking for the derivative of A here. So W, which is 3 times the derivative of length, -1/2. Then plus here, now the length here, which is 2, times the derivative of the width, which is 4. So here I've got -3/2 plus 8. So now to simplify, that's the same as -3/2, but plus 16/2, right? Because that's 8. So the derivative of the area with respect to time is changing by 13/2. So here's our mass is equal to force over acceleration. We are going to find the derivative. Oh, sorry, that is a typo. We're looking for a derivative of m. So mass here. So again, here we've got mass with respect to time. Notice though, quotient rule. So here we go. We would take the derivative of the top, which is just 1. So that was just 1. So with respect to t, times the bottom. So times a. Minus now the derivative of the bottom, which is just 1. So the derivative of the bottom times the top. So that's f over a squared, the derivative of the denominator to the second power. So now substitute. We've got here a, which is -2 times the derivative of our force. Derivative of f is -1 minus f, our force, which is -3 times the derivative of a, which is 6 over a, which is -2 squared. So now notice here we are just simplifying. I've got 2 plus 18 over 4, 20 over 4. So the derivative of our mass with respect to time, the change is 5. Go ahead and pause the video and try this try on your own. And here we go. So here we're finding derivative of A, our area with respect to time. Notice, again, this is product rule, B times H squared. Derivative of B is just 1. So 1 times H squared is H squared. But we took the derivative of B. Then plus, now the derivative of H. Well, that's 2H times B. That was the derivative of with respect to time. Now we're going to substitute. Oh, again, sorry, that was a typo. That was supposed to be B here. So now we've got the derivative of A with respect to time, derivative of area. I've got H squared, so H is 2 times the derivative of B, which is 1, plus 2 times H, again, which is 2 times B, which is negative 8, times the derivative of H, which is 3. Now simplify. So here I've got 4, then 2 times 2 is 4. That's times 12. 12 times negative 8, negative 96. So the derivative of A, so the area is decreasing with respect to time because it's negative 92.